This is an introduction to differential equations, and we're going to be talking about solutions and initial value problems. Sometimes we call those IVPs. Okay, let's first talk about what an nth order differential equation is. So an nth order differential equation is an equality relating the independent variable to the nth derivative, and usually we'll have lower order derivatives in the equation as well. And these are of the dependent variable. So here you can see that we have f, and it's a function of x, y, and the derivatives, all the way up to the nth derivative. And here we have order n. So this differential equation is of order n. So this DE has order n. And likewise, we can write the equation isolating the nth derivative and say that that nth derivative is a function of x, y, and all of the derivatives up to the n minus 1th derivative. So here we have just solved for this nth derivative. And this is really the preferred equation. Okay, let's take a look at some examples. Here you can see that we have a second order differential equation. So we have order 2, and this is an ordinary differential equation. And here we have that x is the independent variable and y is the dependent. So y is a function of x. And in this second equation, we have order 2 again because of this second derivative there. And we have t as our independent variable and y as our dependent variable. And again, we have an ordinary differential equation. And in this fourth example, we have order 4, since that fourth derivative appears and in the equation. And we also have x is a function of t, and again, we have an ordinary differential equation. Now, we are going to be solving differential equations, and it's important to know what an explicit and also what an implicit solution is to a differential equation. So we're going to start with an explicit solution. And so we have a function phi of x that when it is substituted for y into the equation, and you could substitute it either into this first equation or this second equation, and I also have them written down here. So when we substitute this proposed function or this function, phi of x, that it satisfies the equation for all x in the interval I. And this is called our explicit solution. So we have this open interval I. And so basically I says that x is between A and B, and A and B could both be infinite. So we just have this open interval, and open is really important. So I is an open interval. So an explicit solution satisfies, that's a really important word, satisfies the equation. Let's go ahead and do an example and see if we can make some sense of this. Show that phi of x, which is equal to x squared minus x to the negative 1, is an explicit solution to the linear equation shown there below, but psi of x equals x cubed is not. Okay, so let's go ahead and try to satisfy this DE. Okay, and of course this is a linear DE, and as you can see why, that we have additive our derivatives and our functions are added together and not multiplied together anywhere. And so what do we need to do? We need to find, let's go ahead and use phi of x, and let's go ahead and find that first derivative. So let's rewrite this. This is x squared minus x to the negative 1, and let's find that first derivative, and that's going to be, and actually I need to change that. I can write it either way. Okay, and that's 2x, and then we have plus x to the negative 2. I'm going to go ahead and leave that. And then, of course, we need to get to the second derivative, and that's going to be equal to 2 minus 2x to the negative 3. So let's go ahead and all of these are defined when x is not equal to 0. And of course you can see here x not equal to 0. Okay, so we have our second derivative. So we have the second derivative of y with respect to x. And we're going to go ahead and plug those in. So here our second derivative is x squared minus x to the negative 1. Whoops, that was not my second derivative. Just go back. We need that 2 minus 2x to the negative 3. And now we're going to subtract 2 over x squared. And now this is our actual function, x squared minus x to the negative 1. And then we are going to say that that is equal to, or check to see if that is equal to 0. Okay, let's do some simplifying. So we have 2 minus 2x to the negative 3, and this would be minus 2 plus 2x to the negative 3. Okay, we're going to see if this is equal to 0. And as you can see, we have our terms cancel, and we have 0 is equal to 0. So therefore, this is valid for any x that is not equal to 0. And so we do have that phi of x. Therefore, phi of x is an explicit solution to the DE. Okay, and so now we want to do the same thing, but now we're going to look at psi. So I'll go ahead and write that psi of x is equal to, what do we have here? X cubed. And so let's go ahead and find our derivatives. 3x squared, and we have 6x. Put this back, make that a little bit bigger. Whoops. And so let's rewrite our differential equations. So we have the second derivative of y with respect to x minus 2 over x squared y is equal to 0. So our second derivative is 6x minus 2 over x squared multiplied by our function is equal to 0. And so we have 6x minus 2x is equal to 0. And that is equal to 4x. And that is definitely not true. So, therefore, psi of x is not a solution. Okay, so moving on, let's look at our next example. Show that for any choice of the constants C1 and C2, phi of x, shown there, is an explicit solution to this linear equation. Again, we have a linear equation here. And we want to go ahead and find our derivatives of that function. So let's go ahead and do that over here. So I'm going to rewrite phi of x. Okay, and so our first derivative is going to be negative c1 e to the negative x. And then we have plus 2c2e to the 2x. And so, looking at our second derivative, we will have a positive c1e to the negative x, and then we will have plus 4c2e to the 2x. Now, we're going to go ahead and substitute those in to our given dE. So I have c1 e to the negative x plus 4c2 e to the 2x. So that's our second derivative minus, so I'm going to go ahead and have to do that on the next line, minus, and we have our first derivative, opposite of c1, e to the negative x, plus 2c2, e to the 2x. And then we have minus 2 times, and now we'll go ahead and plug in our y, which is c1, e to the negative x, plus c2, e to the 2x. And we're going to check to see if that's equal to 0. Let's go ahead and factor out an e to the negative x. So if we factor out an e to the negative x, we're going to grab these terms. So it would be this term, and this term with their coefficients. So we have c1 plus another c1, and then minus 2c1. So we've grabbed those. Now let's go ahead and factor out an e to the 2x. And where you're going to find those is here. Don't forget about your negative in there. So let's go ahead and do that. We have 4c2. And then here we have a plus minus 2c2, and then minus, again here, this 2c2. And we're going to see if that is equal to 0. And as you can see, we have here, this is equal to 0. That's 2c and that's 0. So we come up with 0 is equal to 0. And so we can say that phi of x is an explicit solution to the DE. Move this over here. Okay. Okay, now let's look at another example. Show that the relation y squared minus x cubed plus 8 equals 0 implicitly defines a solution to the nonlinear equation. So basically, let's first talk about what an implicit solution is. So here we have a relation, and it basically is a function of more than one variable. And so basically these solutions are embedded in a given solution. So let's take a look at this real quick. So you can see here that really we would like y, but y is embedded in this equation, okay? So let's go ahead and see if we can solve for y. Sometimes we can't, but in this case we can solve for y. So here we have y squared is equal to x cubed minus 8. And so we have y is equal to plus or minus the square root of x cubed minus 8. So let's go ahead and see if this function is an implicit solution, or now we would have an explicit solution to this given differential equation, okay? So if we go ahead and try, and we'll go ahead and let that be 5x is equal to, and we could just start with the positive root, x cubed minus 8. And here we're going to just need the first derivative. So, or we could write it y prime. And here we have 1/2 x cubed minus 8 to the negative 1/2 times 3x squared. So here we have 3x squared over 2 times the square root of x cubed minus 8. Okay, and so here you can see that our interval here, 2 to infinity, of course we want x cubed minus 8 has to be greater than 0. X cubed is greater than 8, so x must be greater than 2. And so that's where we have this interval from 2 to infinity. Okay, so now let's substitute these in to our differential equation. So we have 3, I'll go ahead and write that again. We have dy dx right here is equal to 3x squared over 2y. And so our derivative is 3x squared over 2 times x cubed minus 8. And let's see if that's equal to 3x squared divided by 2 times our function right here, which is the square root of x cubed minus 8. And as you can see, whoops, and I had to have this 2 down here from this 2. So as you can see, these are equal. So now we can say that phi of x is a solution, and that's an explicit solution to the differential equation. Now, what's really important, you can also check psi of x equals, that negative root. And I think that was as x cubed minus 8. It will, this is also a solution. Okay, just wanted to go back up right here and remove that circle. Okay,